what you're interested in, and it looks like we have a majority for mechanical engineering, so I will have lots of stories to tell, since that is my background as well. I think it's coming. It's coming. It's just a delay. Okay, there it is. And there I am. So, welcome. I am Professor Markt, and instead of the usual classroom lecture, today I'm going to talk a little bit about my experience working in industry before I came here to Kenyatta as a faculty member. So my background, I have a bachelor's in mechanical engineering, and I have a dual master's in systems engineering and also technology strategies of business as well. So my first question for you is, why do we send objects into space? TV, good. And observe, what do we observe in space? Yeah, comets, planets, stars. Weather patterns, yeah, who watches the weather on news to see what the forecast will be? Good. Yeah, so we benefit from weather forecasts. Who has a cell phone? Yeah, those are pretty useful. How many of you have used GPS to get to your destination? Yeah. So we use spacecraft on a regular basis in our daily lives. It's very useful, very fundamental, right, to how our society operates today. We use these things all the time. Okay, so we're going to do a 10-second history on space. So how did this all begin? We started in 1961. So President John F. Kennedy announced to the world that we were going to send a man to the moon. And sure enough, eight years later, in 1969, Neil Armstrong and Buzz Aldrin landed on the moon. Mission accomplished. So now, who is in this picture? And who else? Buzz Aldrin. So Buzz Aldrin, the astronaut, and me, the aerospace engineer. And I like this photo because it's not so well refined, right? We're humans. We're just humans smiling in a picture together. And the point is that sometimes when we talk about engineering, or we talk about things in space, it sounds so far away, right? And so, yeah, somebody did that. But it was somebody really far away that did that. But no, if you choose to study engineering, you get to be one of those people that does really cool things, right? We're real people, just like you. And on to the realness. I was stretching. I tell so many stories in class. I was trying to think of something I haven't told you in general already, so I thought for sure I haven't told you about high school. So I started in San Jose, East Side San Jose, not so far from here. I'm a local. Independence High School, some of my favorite things to do, I was on the swim team and I like dancing. I danced for 16 years or so. I loved it. In addition, when I was in high school, I was in the Space Science Technology Magnet program. So my history class was history of space. And my electives, I learned oxy-acetylene welding. I didn't, unfortunately, get a photo of myself welding, but that's the general idea. It's a pretty cool big torch if you get the oxygen percentage just right. And one of our design projects in high school was to design a watercraft out of cardboard and tape, and then race it across the school swimming pool. And some of us sank and some of us floated. Fortunately, mine floated and made it quickly to the other side. But starting out from a fairly young age, I really enjoyed this process of inventing and creating things and being creative and seeing what we can build. And another message here. So So east side of San Jose has a few things in common with maybe east side of Palo Alto. It's actually not the most ideal neighborhood to grow up in. And the message here, the thing that I love about being in America, being an American, is it doesn't matter where you start. You can do anything. The world is open to you. So then I graduated from high school, moving right along, and I went to college, and I chose to study mechanical engineering. So the picture on the upper left is my capstone design team. We had a year-long senior design project, and our official final project was the recumbent cycle on the right, which was a fun project because then we got to ride it around when we were done. So a couple of things about the bike recumbent cycle we designed is that it has 2 parallel tubes, and we designed it so that the drive chain, bicycle chain basically, goes inside of the frame. And so that way you don't get grease on your hands when you're riding it around. And we actually patented that idea. So on my way to becoming an official engineer, right? Another contribution to the recumbent cycle was a 2-leaf glass fiber suspension system. So the front 2 wheels have suspension literally made out of glass. So I did the analysis, I designed it, and then I also built it. We had an autoclave on campus, which is like a really big oven, and it's called laying up, but you lay down the glass fibers and put it in a bag and pull a vacuum, and then you run a thermal cycle and alternate temperatures until it solidifies and you have a solid glass fiber part. And indeed, when I was in school, I loved material science. I thought materials were fascinating. And so the next photo over is an example of 20 in copper, which I'm really starting to geek out now, but if you're in my material science class, you would appreciate this, that your atomic level, your atoms, have these crystal structures, this organization, almost like Legos, right? They go in a certain place, and sometimes they shift and they change orientation, and here you have mirroring, so they exactly mirror in a pattern, and the grains kind of go back and forth. But this whole idea of understanding how atoms fit together and how it impacts the strength of your material, I thought was really cool, mostly because I think it's really fun to break things. It's really fun to design, and it's even more fun to break it and see what'll happen. So then I graduated. What did I do after graduation? My very first job out of school was in the oil and gas industry. So on a deep sea oil rig, there's a drill. And on this drill, on the tip of this really long drill, there's synthetic diamond carbide cutters that have the diameter of about the size of a quarter. And that is my contribution to the overall oil rig, was those diamond cutter parts. So what did my work environment look like? What was the equipment I was working with? We had thermal chambers to purify the diamond powder and carbide metal components. And we had hydraulic presses to load parts into a casing and a pressure chamber to transform diamond powder into a solid diamond. And if you look at the chart on the left, you can see at what point graphite, which is like your lead or pencil, how does that turn into diamond? They're both made out of carbide, or carbon. Pardon me. They're both made out of carbon. The difference is what conditions they've experienced. So if you take graphite and you apply a high temperature and a high pressure, it turns into diamond. And that's how you make synthetic diamond. And if you'll notice, high temperature is actually reaching the melting point of metal, which means it's really hard to find a container to hold this powder because your container will melt, and that's a problem. So we push the limits on how high we can raise the temperature. And then we also have a rather high pressure. So if you try to think about what does it mean to have 60 kilobars of pressure, that's the equivalent of a 160-mile high column of granite. It's a lot of pressure. So a lot of temperature, a lot of pressure. So it's a very specialized manufacturing process to make this synthetic diamond. Okay, so what did I do exactly? Right? What was my contribution to all of these things? So my job was to look at how to automate the process, because we had a lot of defect parts when people were making these by hand, one at a time, very manual process. And so we wanted to improve the quality, and so we were looking for ways to introduce automation and reduce how much wasted material we had. Another part of engineering that you don't necessarily learn in school, but I can almost guarantee you will learn this on the job, is how to select a supplier. So, let's say my refractory brick cracked, or my thermocouple went out, or, oh, I need some new tubing. Where are you going to buy that? Exactly. So that's actually a noteworthy part of your job is identifying what parts you need and where you're going to find them, working on pricing agreements, that sort of thing. I did programming, so I needed to control we had to pull a vacuum to get the air out and backfill, so put a different gas in for the chemical reactions we were looking for. And then we had to heat it up and cool it down, and that's all controlled by software, by writing code to run the equipment. And last but not least, I created drawings using ProE to design custom tooling and equipment. So how is that interesting for you? That means that what we're learning here at Kenyatta is useful. So, which is great news, right? That's what we want to know. So the first one, process engineering, learning how to improve quality. I have taught a lot of these concepts as part of Engineering 100, and I plan to do even a little bit more of that, because it's not normally taught in school. So you learn a lot in hindsight, right? You go through school, get some work experience, and come back and you realize, oh, I didn't learn that in school. So I'm trying to fill in some of those gaps for you. And Engineering 100 is a great spot for that one. Procurement, I'm not sure how to help you too much on that one, unless a design club, right? Join Yardley, you can help them find parts. Material science, Engineering 270 is very useful, and this is an example. This is our class. So if you're in this picture, raise your hand. Yeah, so we went to Stanford. Actually, Stanford came to us. Stanford came to us and explained how they make silicon wafers, which then turn into computer parts, processors, as well as nanomechanisms. So on the atomic scale, they actually locate individual atoms to create mechanisms, nanomechanisms, very cool stuff. And after they explained to us what they do, then we went to Stanford and we got to see their equipment and see how they do what they do. And the image on the left is another student project. So that's when I taught graphics design. And one of my students decided to model a MiG-25 interceptor. He was really into that class. So he did an excellent job, and that is actually only the aircraft. He also did the whole photo rendering with the sky and the city in the background, and it was pretty awesome. So yeah, graphics design can be a lot of fun. Next job. So after Novotech, I moved on to Lockheed Martin Space Systems Company. So these are examples of programs I worked on while I was there. The first one is the Orion Crew Module, which is the next generation space shuttle program. The one on the left is the Atlas launch vehicle, which is now part of ULA. That is how we get our payloads into space. Payloads, aka satellites, whatever objects we're trying to get into orbit. And then on the bottom, we have our James Webb Telescope, which is our next version of Hubble. So I got this great job at Lockheed Martin, and I was so excited. And when I showed up, the first thing they had me do, my first job assignment, was to do metrics, which meant I was collecting data and creating graphs in Excel. So, thus this calls for Dilbert in times like this. I actually had a Dilbert calendar on my desk at all times. So I didn't have any accurate numbers, so I just made this one up. Studies have shown that accurate numbers aren't any more useful than the ones you make up. How many studies showed that? 87. So I show this for a couple of reasons. The first one is it's good to know that as part of the culture of an aerospace engineer, you know you've met one when every other thing that they say is a joke. And typically they say it with a straight face, but it gets to the point where you can't even follow what they're telling you anymore because you're laughing. They are a really fun group of people. And I tend to be sort of cheesy that way too when I teach my classes. It just sticks. Second reason I share this story, well, because it's true. Sometimes when you get your foot in the door with an internship or a brand new job, sometimes that first job they give you is actually not very exciting. It happens. And it could happen to you. And so what I did in this case is it actually turned into an opportunity. So my job was just to gather the data and create the graphs. But the data I was collecting, part of the data I was collecting, were called engineering cause codes. So every time an engineer would revise their drawings, they had to explain why they were revising them. And so management inquiring minds wanted to know, why are we changing this? Because it costs money if you have to change your design. And what they do is they look for trends. So if their engineers in the company tend to be making the same mistake over and over and over, then somebody in management's going to say, okay, we need training, we need a memo, we need some sort of message to go out to our staff to say, don't make this mistake anymore, do it this way instead, or watch out for this one, so that we can reduce the number of changes we need to make. So I was in this very interesting position where I got to see data for the whole company, what sort of mistakes were being made on a regular basis. And I saw an opportunity related to model-based design. So at the time that I was hired, most of the engineering was created, it was created in 3D model, and then they would create a drawing, and then they would print the drawing on a piece of paper. They would get a rubber stamp, and they would literally stamp the drawing and say, that is my official released drawing, and it would go into a filing cabinet. So it was a paper-based engineering system. So they were designing amazing products with a really sort of old system to do it with. And so I went to my management, my director, and I said, I see an opportunity. I would like to come up with a consistent way of creating these models and then release the 3D data, make that the official record of authority, so that now we don't have all these errors that are associated with drawings, the things we overlook, or the model not matching the drawing, or some of the really common mistakes that were being made. And the computer-aided tools were already fairly well developed, right? So if you had a high-fidelity, mostly accurate model, then you could use it for things like a thermal analysis or fluids. Air is considered a fluid, so aerodynamics and fluids are the same thing. Mass properties, how much does it weigh? Stack-up tolerances, so things like the James Webb Telescope, where you have optics. And you have a mechanism because it's stowed when you launch it, and in space, it deploys. So you have a mechanism, it's going to vibrate, it's going to get launched, And now it has to be perfect in space because it's optics. You can't have any error, right? Very small margin of error. So they spend a lot of time looking at tolerances and tolerance stack-ups. And so something that used to take them a couple of months with a model-based tool would take them, a day or two. So when we introduced this, it was like Disneyland for aerospace engineers. They were so excited. It was the coolest thing they'd ever seen, was this model-based stack-up tolerance tool. So it was a really big deal to bring this capability to them to where they could really take advantage of the tools. So what did I do exactly? So we talked about the company, we talked about generally what I was doing, so what exactly did I do? So I ended up being in a role where I had to put together reports, right? Your favorite thing, I know. Your favorite assignments in my classes. I created proposals, presentations, reports to say, here are the errors we're making, here's how we can avoid them, and here's our plan for how we can transition to this model-based environment. So I was involved in the technical piece of understanding how do you inspect the 3D data. If I have an airplane wing that has a contoured surface, how am I going to inspect that? You inspect it using the 3D data. You scan it and collect your data points and then map those measured data points to your 3D model data points. And so everything's connected. So I had to understand all of those different use cases so that I could come up with a standard that would address everybody's needs in the whole company. So once I understood how all the different types of engineers do their jobs and what they needed, then I wrote many standards. I wrote company standards, corporate standards, the ASME standard has my name in it, I'm famous. It's in the front cover. And I also, after several years with ASME, they invited me, so then I was the United States for the ISO standard for 3D modeling. So that view of Mount Fuji was the view from my hotel room, and this is the faces behind the ISO standard. And I'm the one in green. I didn't get the memo on what to wear, I guess. So how is this useful? So how is this related to what we're doing here? So graphics design is just fundamental to engineering. It's one of those classes that I can almost just guarantee you're going to use it in some capacity when you start working. So that class is especially useful. Statics and dynamics. Those are often used in aerospace because you need to understand your mass properties, your mass moments of inertia when you have rotating spacecraft that need to do some type of a high precision task. And I included the example on the left. So this is what they call a lesson learned. There's an official name for this. So there was a program for a Mars orbiter that was supposed to observe the environment on Mars. And the Mars orbiter made it through Earth's atmosphere all the way to Mars, so close, and then unfortunately impacted and crashed into Mars. So then you have to do a root cause analysis and say what went wrong. Clearly something went wrong. Well, what went wrong was that Lockheed Martin's engineers used English units and NASA used metric. And so in the software, when it was trying to navigate and decide what to do and where to go, there was a unit conversion issue. Very unfortunate, very embarrassing, by the way. So, you get so far and something so small. It's always the little things, actually, that tend to get in the way. So when we solve problems in statics and dynamics and physics, and they give you units in millimeters, but you really wish they gave it to you in inches because it's kind of annoying to convert them every time, that's why did you do that to you? So that you get in the habit of saying, do I have the right units, right? You're conditioned that way. Because real things go wrong when you don't pay attention to your units. Process engineering, I'm going to continue building that in. So this is our water bottle rocket launcher. And so we will add more process engineering to maximize altitude per launch. Oh no. Okay, so I did so many great things, right? I turned Lockheed Martin from a potentially not so interesting metrics sort of job into a really exciting model-based engineering transition sort of job. And I was on a roll, so I decided I would go to MIT for graduate school. And what did they have me do? Metrics! I was in disbelief. What do you mean? I come all the way to MIT, and now I'm doing metrics. I worked so hard to get here. Okay, so we will compensate you. We'll pay for your tuition, stipend, if you please do these metrics. Okay, twist my arm. So here I am, I'm doing metrics. And so the metrics are something that the US Air Force was interested in. And the way that they manage their programs is primarily by schedule. Are you on time in delivering your product? And are you on target with cost? So how is your budget going? And then based on those two measures, they decide how well a program is performing. Well, what they're lacking, or we're lacking, was value. Do we need this program? Is this useful to us? We decided to fund it 10 years ago, but do we actually still need it today? So that was my task as a student, was to help the whole Air Force figure out how valuable each program was on a portfolio level, to quantify, come up with numbers that describe how valuable a program is, so that they could balance it not just on, are you performing well with your schedule and your cost targets, but we also want to make sure they're useful and relevant investments. So then I found myself in an experience. So I had to travel and talk to people and learn how does the Air Force make decisions in the investments that they make. And so I even went to DC with my understanding that I was going to go and talk to metrics people and learn how they gather data and create these graphs. Okay, so I go there, and they walk me to a room that just so happens to have a 3-star general and his entire staff. And they asked me, what do you want to know? Oh my God. So I was not quite prepared for that, but it was an amazing experience. So you never know where metrics might take you. So this photograph is my dorm room. Most 2/3 of the way through my thesis, I had this epiphany where all of a sudden I had this newfound understanding that was pervasive throughout my thesis. So I had to find all those pages that I had to then revise and edit and correct. But I did finish it. You can see the completed version in paper clips on the right. And my personal goal for myself, or reward, was the same day I turned in my thesis, I went directly to the Charles River and went kayaking. That was my celebratory measure. So indeed, I did graduation number 2. And the other message for here, so my undergraduate degree, I was very focused. I worked really hard, literally with a job, and I studied really hard. So I learned quite a bit about engineering, but despite so many years in school, I didn't have so many memories really, other than memories of the computer lab and laboratory experiments, which were fascinating. But I decided when I went to graduate school that I was going to have fun. And I highly recommend doing something like that. Because even though I was in graduate school for a shorter amount of time, I joined the sailing club. This is the Nevermore. So we sailed to the harbor islands on weekends that it was not snowing. And I went on a Sloan trek to Moscow with a group of friends. We went to Russia. I went chocolate tasting on a regular basis. And I even saw a Red Sox game in person in Fenway Park. And I'm so glad I did all of those things. So really make the most of your opportunities when you're in school. Remember to have fun. A couple other experiences. So I worked with a small startup called Pavilion Power, and we worked on wirelessly charging cell phones. This particular photograph is for inductive coupling, so it just needs to be in proximity. My startup was from a distance, so from several meters away, you could charge your phone. So just by walking into a room in proximity, which would be ideal in like a cafe or an airport or something like that, your phone would charge without having to compete for the plug with your neighbor. So it's a great idea in progress. The risk is that it might also charge you. It doesn't discriminate between phones and humans. So it is not widely available on the market. The next examples are actually available in industry, per purchase. The next one is a wearable device. So you've probably seen those bands that you can put on and wear, and it'll measure your heart rate and biometrics. This one's kind of built into the shirt so that it's more comfortable to wear. So that's an electronic device. This was when I worked at Flextronics. And then another customer I worked with was Nike. And there's no electronics here. So this was a new adventure, but there's more in common than you might think. So the way shoes are made today are by hand, which is why if you try on a pair of shoes, the right might fit a little bit different than the left. And they might also fit different from the next box of the same size, because there's a lot of variation whenever things are done by hand. So our task was to automate this process and to make it more consistent. But while I'm here, so one of the things you do with the shoe is you have to 3D model it in order to create the patterns. And modeling something like an organic foot shape is actually rather complicated because it needs to be just right. Otherwise, it could be uncomfortable or it could look not right, right? And there are several pieces that are layered on top of each other, so you have stack-up tolerances. And once you get it all modeled, then you have to create a flat pattern so that you can cut it out. So it has a lot of similarities with sheet metal, where you need a flat pattern, they all stack up and go together. So circuits and devices, material science, graphics design, product development, right? All very, very useful skills. And then this one, who went to Flex? Raise your hand. You. Good, good. Okay, so this was last semester with the circuits and devices class and more. It was open invitation. We went to Flextronics and we got to see how electronic devices are manufactured and scaled for higher volume. And then the picture on the upper left is a wind turbine blade, which is an example of modeling and product design. It's one of the projects in Engineering 100. Okay, so here's my time for sage advice. We're getting closer to the end. So here is your plan. And ideally, right, you go from kindergarten to high school to college to a job, and then there you are, you arrived. That's it, right? That simple. But what it really looks like is more like this. Deep valleys, oceans, gondolas, forests, ladders, and perhaps a flag at the end. You never know when you've really arrived. So things don't always go according to plan. So my message here is that life is not so predictable. And not only that, but every person's experience is completely unique. No two of us are going to have exactly the same story. And so my challenge for you is to take what you have and run with it. Make the most of the opportunities that come your way. One of my favorite quotes from Emerson is, make the most of yourself, for that is all there is of you. Lesson number 2 is there are 2 reasons you go to college. 1 is to learn new things, and 2 is to meet new people. We tend to really emphasize the first one. We do our homework, we study for exams, we ask good questions in class, right? We know how to do those things. That's definitely a clear focus. But meeting people is really important too. And that is because when you finish school, you all want to find really good jobs. And right now, the person sitting next to you seems like, oh, yeah, that's somebody in my class. Yeah, we study sometimes. But in 4 years from now, that's going to be someone with a really awesome job at Tesla. And you're going to say, hey, buddy, can you hook me up? Right? So networking has 2 parts. Networking has part 1, which is actually going to formal events, and part 2 is having fun. Because having fun not only creates those fun memories, but it also creates those good friendships, where you help each other out far beyond Kenyatta. And then my last story. So this is my story. When I was in high school, I think I mentioned this in the beginning, back to high school again. One of the things I liked to do was swim. So I was on the swim team all 4 years in high school. And I went to college, and I wanted to try out for the swim team, right? Keep going. So I showed up, and it was an indoor pool, so I looked in the window, and they were pretty good. And I felt really intimidated because they were really good. And so I chickened out, and I didn't show up for the tryouts. And that is my own personal, remember that lost opportunity. Because the only reason I did not swim on that college team was because I didn't try out. It was completely my fault because I didn't give it a try. If I tried and failed, then it would be out of my control. I would have done everything I could have. But since I didn't go, it's on me. And so that's my own personal lesson learned. Whenever I feel really nervous about trying something new, and I'm feeling kind of chicken, remember the swim team. Don't do that again. And so, when I went to graduate school, I joined the swim team. I wasn't the fastest swimmer, but I did it. I was there. I came to practice. I showed up, and I got to swim. So reach high with your goals. Reach high with your dreams, and then go do it. Take advantage of the opportunities that come your way. And that's all I have. A question and answer. I don't know how much time I have.
About 10 minutes.
Okay, there it is, 10 minutes. Any questions? Yeah.
So I understand that you also how do you explain to us like your coding experience. Like how did you learn computer science, and how long did it take you to and take all that knowledge?
Okay. So as a part of a mechanical engineering degree, you do have to take code programming classes. So it's kind of one of those fundamental, there's no escaping computer science sort of thing. And then on the job, kind of as needed, you learn it. Right? Because if something's not working right as an engineer, that just became your job responsibility. And so there's a lot of the on-the-job training and just kind of figuring things out. Yeah, a little bit in school and then a whole lot on the job. Yeah, good. Yeah.
You
You said on-the-job training, you mean on-the-job learning? Are you teaching yourself, or was there someone there that you could ask if you really needed it?
A little bit of both. That depends on the place where I'm working, right? So the first company, Novatech, it's a small startup. And so there were 4 different departments. And in my department, in the Diamond Lab, I was it. I was the whatever needed to happen. And I had a group of production workers, line workers. But otherwise, if we ran out of gloves, that became my job. If the thermocouple went out, that became my job. if the code wasn't running the right cycle, that was my job to fix it. Figure out what cycle should it run and how do I update the code to run the cycle it needs to. So if you work for a small startup, there it is. But then a larger company like Lockheed, when I showed up for work, the first thing they did was send me back to school. So I actually took a class. Lockheed paid me to go to class, and I took graphics design all over again. I took a class called orbital mechanics. I took a class called geometric dimensioning and tolerancing. And I literally sat in a room with a teacher and I had to do homework. So when you're with a bigger company, there's a lot more structured training, and you're assigned a senior engineer who overlooks all of your work, writes all over your drawings, gives you all kinds of feedback. So you have a lot more support. Anything else? Okay, well, thank you for coming.